Okay, just a quick look at what we were doing so far. So far, our main objective has been to deal with the vector field and try to see how much work the vector field does in maybe in R2 or R3. So far, we have mostly done in R2, but if things are easy enough, it's not too difficult to do it in R3. Okay. So the first part there on the top blackboard, that's where we started in 4.2 to compute a line integral along C to compute the work done along that particular curve. And it could be an electric field or magnetic field, and it's doing a certain amount of work in going through a certain curve. And if it is parameterized properly, it could do it in R2 or R3. Could also do it without parameterizing, which kind of works out pretty much the same way if you do it right. And make sure that when you're doing this process, one of these variables should be converted in terms of the other using the curve C, which could be given as y equal to f of x. So dy is f prime of x dx. So if the question is not giving you a parameterized form, and if you don't want to go through that hassle, okay, that is one alternative there. You could always do this. Either way, you should get the same answer. Okay. So that calculation is not too bad if the vector field is kind of gentle enough and if the curve that you're parameterizing is nice enough. Okay. That is just a calculus one integral in terms of t or x. And on a nice sunny day, it's not a difficult thing to do. But I think at some point we decided, okay, it's something else we could do with it. And I showed you an example where there was a vector field that's connecting, or we took two different paths, C1 and C2, between 0, 0 and 1, 1. And I think the vector field looked like this: 2y minus x square and 2x minus y square or something. I think that is what it looked like. It was one of the examples in worksheet number 12, the last one. Our main observation was that irrespective of which path you took, you did the same amount of work. We did that using our traditional way, and I think the answer came out to be 4/3 for C1 and C2. And that is what we call as a conservative or a path independent vector field. So by definition, you should be able to find some potential function so that you can represent the vector field as a gradient of that potential function. So it's called a conservative or a path independent vector field, also called a gradient vector field because this is the gradient vector. So it's all the same thing. So the requirement for a 2D vector field to be conservative is that there should be no rotation inside or rotation that is around that curve C. Okay. So the two-dimensional curve, which is actually a measure of the rotation of the vector field, is equal to 0, and that is a necessary condition for the vector field to be conservative or path independent. If you can guarantee that, you could evaluate this scalar potential function, which is a pretty straightforward process. Okay, it's a very reliable process actually. If you just do it step by step, you will end up with a function f of x, y. Okay. The advantage is that then you don't have to integrate it along each point on the path. You can just focus on the starting and final points of that curve and use the scalar function to see how much potential has changed between those 2 points. Okay. And the easiest example, if you are lifting a weight from, say, height h1 to h2, in the absence of anything else, the work then in pushing something or lifting something from this height to this height is the difference in potential energy between those two heights. Okay. And that gravitational force is a conservative vector field. It doesn't matter which path you take. You could lift it directly up, or you could take stairs, or you could take an elevator. Okay. You do the same amount of work as long as there is nothing else going on. So that is the concept of a conservative vector field. I know it's a lot of writing here, but the key part is this one. Okay. This is the check if a 2D vector field is conservative or not. That means there should be no curl component or rotation component to it. And If this is true, then it's worth investing time to find this. Okay. If this is not true, don't do it because you cannot find it. So that's where we stopped. So since I think students are slowly getting in, I'm going to just do this as an illustrative example for how to find the potential function, just to convince you that you're doing the integration along this path, that path, or using that theorem there, which is called the fundamental theorem of line integrals. They will all give you the same answer if we are working in a conservative vector field. So that's what I'll do first, and then I'll let you do the problem that is in your worksheet number 13. All of you should be able to do this. This is a very simple exercise, actually. Okay, it's probably one of the easiest things you could do in chapter 4. So I'll do the first one myself, and then let you do the worksheet problem yourself. And there'll be one question on tomorrow's quiz for those of you writing it. Okay. So you can get some practice there as well. And I'll guarantee that there'll be one such on test number 3 as well. If you don't know how to deal with a conservative vector field in calculus 3, it's kind of pointless. Okay, before I erase any of these, do you have any questions? That's a whole lot of things there. Yeah.
Are we only dealing with vector fields in R2?
Not really. I mean, R2 is the easy one to do. I think I have one exercise in R3. You could do that as well. But R2 is the one that you can easily compute. Any other questions? I should open the chat window here. All right, so I'm going to quickly do example 1. So the vector field f of xy equal to 2y minus x square and 2x minus y square. Okay. This is the same vector field that you have in that problem in worksheet number 12, number 4. So I think that's the same thing. Good. And let C be a curve. Now I don't care what shape it is because I'm expecting a conservative vector field. Okay. So it's a curve from 0, 0 to 1, 1. So it's oriented, it says it's starting there, ending there. So question 1, is f conservative? Sometimes the question may not even ask you is f conservative, it will just expect you to first check that condition because it will save you a lot of hassle. Okay. So is f conservative? Then part 2, if f is conservative, find the potential function little f. And part 3, find the integral along C f dot dr. And when you see this third question along with questions 1 and 2, you should know that these things are related. So don't start integrating this in a completely different way. Okay. So the whole point is that 1 leads to 2, 2 leads to 3. Okay. And for our reference purposes, let's call this P and this is Q. So I think whatever I've written there is probably the useful part. Okay, kind of goes step by step. Step 1 there, start with fx equal to p. Then step 2 here. That's what we are trying to do in all these conservative vector field problems. Let me just lower it a little bit. So this is equal to, well, first let's verify this. Okay. Is qx minus py equal to 0? Not qy minus px. Okay. That may or may not be equal to 0. We don't care. Please don't check the wrong thing. Qx minus py, the cross component. There should be no rotation in this if it is conservative. qx is 2, py is 2. Okay. Oh yes, that's 0. Not I know it's an instinct to probably go q with y and p with x. It's the cross component. Okay, so now we can invest some time into finding this little f. So let's write 2y minus x square, 2x minus y square equal to partial fx and partial fy. That is a requirement for this being a conservative vector field. For some scalar function, that vector field must be the gradient of some function. We don't know what the function is, but that's what we're trying to find. So let's go through that process there. Start with fx equal to p. Not going to write step 1 and step 2, but just following that process. Partial fx equal to 2y minus x square. Integrate both sides with respect to x, okay, f of xy. Since you're doing with respect to x, y is a constant, so it's going to be 2yx minus 3/3. And please don't forget to include the constant in this case, which will be a function of y. Okay. So it is some f of xy, but it's not complete because we still don't know what this guy is. So that is the end of step 1 there. Integrate with x, get some incomplete form for f of xy. All right, now start there and then take its partial derivative with respect to y. Keep your work organized so that you don't keep looking at the wrong places. So wherever you just stopped in the previous step, start from there. Okay, so find partial fy. Previous step. Well, if you make the mistakes with partial derivatives, it's going to make these functions look very awkward. Okay, so partial fy would be 2x. There is nothing from the middle term because there is no y there, plus g prime of y. The derivative of y is 1, so it's 2x minus 0 plus g prime of y. And this must be equal to q, the component that we did not use earlier. Okay, and that is what I have written here, set fy equal to q. So this is equal to 2x minus y square. And if you did your math correctly, the only thing that should remain at this point is a function of y on both sides, okay, because g prime of y does not have any x in it. So all the x terms should cancel out, any kind of cross terms should cancel out. So you have g prime of y equals negative y square. So g of y is the integral of this, which is negative y to the power of 3/3 plus some constant c. Okay, so now we have it. So f of xy equal to that step plus the g of y up we got here. So that's going to be 2yx minus 2yx or 2xy minus x to the power of 3 over 3 minus y to the 3 over 3 plus c. Okay, it's a scalar function. There are no components here. This is just some surface in the xyz space. So once again, it's worth finding this function because now if you know the initial and final points, okay, integral along c of f dot dr without doing any integration here, it's going to be f of 1 1 minus f of 0 0. I didn't care how you go from 0 0 to 1 1. Okay. So this c is a curve from 0 0 to 1 1. That could be a straight line or a parabola or some kind of weird shape. I don't care. F of 1 1 is 2 minus 1/3 minus 1/3. And x equal to 1, y equal to 1 plus c. The c's will get cancelled off anyway. So even if you don't write it, that's okay. Minus f of 0 0 is just 0 plus c. So you get 2 minus 2/3, which is 4/3. And I think that is the answer we got yesterday by integrating along each of those paths separately. For this problem, it might look okay, I could have done the other way, but there are vector fields which you don't want to deal with directly. You could just use your potential function and subtract it out. So it's a very reliable process. The nice thing is, if you have a vector field and you know the 2 points there, okay, this always works. There's absolutely no concern of this giving you a hard time anywhere if you don't make any mistakes. All right, any questions on this one? So, there's absolutely no excuse for getting this wrong or not able to do this. Okay, so let's do the next problem in the worksheet, which is worksheet number 13. Okay. I did one of them yesterday, but then this is your chance to do one. Problem number 2. Should I project it here or do you have one? No. Even in an ij notation, you could just write it as components if you want. Okay. F of xy equal to 2x e to the y and x square e to the y plus 1. So what do you think is F conservative? If that answer is no, it's a really sad situation. Is it? Okay. So qx is 2x e to the y, py is 2x e to the y. If you're getting that answer to be not equal to 0, please double, triple check your work. Okay. Hope all of you agree with my integration with respect to x here. Okay. You could also integrate q with y, but you just have to do the opposite of what we've been doing. So just stick to one method, always works. So from here, find partial fy. What is partial fy here? From there, okay, not from the q. This one. What is partial fy from here? Okay, good. X square e to the y plus g prime y. Thought I heard something very dangerous before that. Okay. All right. What should we do next? Yep, set this equal to q because q was fy to start with anyway, right? So it's a circular process. You start somewhere and you kind of reach back at what you were initially given here. Okay. Just for keeping the flow of steps here, I'm going to write it below this. And Fy is also equal to x square e to the y plus 1. Because you cannot just abandon that other component just because you started with this. At some point you have to make use of that. So these two are now equal. Okay, so my promise is that any unpleasant or troublesome terms must cancel out. Because the left hand side only has y, the right hand side must not have any x terms in it. So both those cancels out. G prime of y is 1. I'm tempted to write g of y equal to 0. Is it? If g prime of y is 1, what is g of y? When things get easy, it gets more confusing, right? Y plus c. So y is kind of correct, y plus c. It's certainly not equal to 0. Okay. You're taking the antiderivative, so the derivative of g is now 1 plus 0. Okay, so now we have all the things we need to fill up your f of xy. So this is your g of y, so f of xy equal to x square e to the y. Kind of a bad place to write that. F of xy equal to x square e to the y plus y plus c. If you find its gradient, you should get the vector field that is given in the question, and it works both ways. Any questions up to there? On Zoom. Okay. Now you did all this hard work, you got this nice function. Okay, the whole point is you don't want to make your life a living nightmare in part C. Okay. So part C must make use of this instead of going and doing all kinds of crazy integration with some bizarre vector field. Okay, so part C is telling you that you're moving a particle along a curve which is parameterized by r of t equal to 4 t e to the power of t and t square for 0 less than or equal to t less than or equal to 1. Okay. I know you're dying to do that integration, putting this r of t in that f of xy. You can see what kind of horrible things will come out of that one. Okay. You don't want to do that. The reason why you found this function is so that the integral along c of f dot dr is the difference in potential between these two terminal points. Okay. So f of r of 1 minus f of r of 0. I have very little interest in knowing what kind of shape that curve has got. Okay. F of r of 1 is the final point because this is the curve that defines it. So r of 1 is, you plug in t equal to 1, this will give you 4e and 1. Okay. Four times 1 times e, 1 square. And r of 0, which is the value where it was starting in time, would be 0, 0. That is all you need to do with that parametric form. It's nothing to do with integrating it or making your life more complicated. Okay. So just extract the starting point and the finishing point and plug it in here. This is going to be little f at 4e 1 minus little f at 0, 0. Okay, now when I say little f, that is referring to this function here. That's going to be x square e to the y. So it's going to be 4e square e to the power of y, which is 1, plus y, which is plus 1, plus c, which is going to get cancelled out anyway, minus f of 0, 0, which is going to be 0 plus 0 plus c. Don't assume that this is always going to be 0. It could be something depending on the function, but in this case, the 0. Okay, what is this? 16 e to the power of 3 plus 1. Right? And don't touch that calculator to find e to the 3. So usually that part C carries 1 or 2 points. So that must be a hint that you shouldn't be dealing with any kind of monstrous integrals or anything. All right. So up to there for quiz number 4 tomorrow. Okay. So you'll get a chance to do one of these creatures tomorrow. Any questions? Okay, now the question that he was asking, what about vector fields in R3? Well, if you understood what we just did, it shouldn't be too bad, though a little bit tedious. Okay. So what we saw was this, that if f equal to pq with no rotational component, which means that qx minus py equal to 0, that is the 2D curve. Okay. So everything is just going through and it's not curving around. If that is equal to 0, then this is conservative and life is good. Okay. That is what we just finished doing. Now, what do you think if I had a vector field in R3? What will change here? This was a 2D curl for R2. What will be the corresponding? The 3D curl is equal to 0. The only difference is that the 3D curl is a vector. Okay. So this is conservative. If the curl of f in R3 is equal to the 0 vector. Now you have to do that entire determinant business. You have to find each and every component, make sure that all of them are equal to 0. So remember how we did that? The curl of f is I, j, k with the operator terms in the second row and PQR the third row. Either you could plug in those components into this last row here and do it out one by one, or you could just evaluate this first and then check it out. So this is going to be I times Ry minus Qz. That is the first component. The second component is a negative component, so you have to kind of flip it around. Okay, so it's Pz minus Rx. And the third one is Qx minus Py, which is what you had there. So in a way, you are just checking that each of these partial derivatives are the same. So are these equal to 0 or not? If it is, then the vector field is conservative, and we can do a similar process there in getting a suitable potential function and making our life easy. So the reason why this is not a very popular question is it just makes the problem longer. It's not doing anything conceptually more attractive. Okay. So once again, the important thing here is that irrotational fields, curl is a measure of rotation. So irrotational vector fields are always conservative. It's a completely different story if there is some kind of rotation involved, and if the vector field becomes non-conservative, okay, we have no idea then what's going on. There is nothing intuitive going on there. Right now, things are pretty much under control. Okay, so if we take the next problem in the worksheet, which I've kind of kept as just for practice, okay, I'm not going to test you on that one. So if you can take number 3 and check if all those individual components of the 3D curl are equal to 0, then that will be a good starting point. I know that's a lot of things to write, but it's just long, it's nothing complicated. X, Y plus Y. I copied it right. You only have to find the cross partial derivatives. You don't have to find px, for example, py and pz. Okay. Yeah. So once we confirm this is conservative, we can the same process, just have one additional step. What's that doing? QZ. So that's going to be X. So you could either fill it in the determinant, it might look a little lengthy, or you could just write down these partial derivatives and compare it appropriately. Okay, Ry is x plus e to the z. I'm just going to use similar shapes to compare. Ry, qz. Okay, that is good. They are equal. Pz and Rx. All right. Something is not right here. Qx and py. Yeah. Okay. Was looking at the wrong thing. Sorry. Let me put it in a cloud. So those pairs are all equal. Okay. Ry equal to qz, Rx equal to pz, and Qx equal to py. So yes, the answer is conservative. What's the only difference between R2 and R3? Just have to have an extra component here, partial fx, partial fy, partial fz. So earlier we had just two components, two there, three here, three there. Start with fx equal to p. That gives you fx equal to yz plus e to the y plus x. Integrate with respect to x and you get f of x by z. Don't forget the integral of yz dx is x by z. That's a constant. Integral of dx is x. Okay, so you have x by z plus x e to the y plus x square over 2 plus what? This is the only difference between the 2 and 3 variable case. What should be here? G of yz. So if it is a 2 variable, it will be g of y. 3 variables, you have g of y, and that whatever extra variable is there, that is z. All right, keep doing the next step. Find its partial derivative with respect to y. That will be x times z plus x e to the y plus nothing plus partial g with respect to y. Okay. It is not g prime y because there are two variables there. So technically it's a partial derivative g with respect to y. And that should be equal to q from there. Once again, at this point, all the x terms should cancel out because g is only a function of y and z. Okay. So xz cancels here, x e to the y cancels here. So partial of g with respect to y is e to the z plus y square. So you're partially integrating g with respect to y. That's y e to the z plus y to the 3 over 3. Plus some function of what? Z, okay, because we are cutting it down by one variable at a time. So we had 3, got 2 here. Now it could be one remaining variable. So some function h of z. So you can see why the 3 component case is less attractive, because you're doing the same process, nothing new here conceptually. So now you have to write your f of x, y, z each time, because that's where the function gets reset. Okay, so f of x, y, z equal to x, y, z plus x e to the y plus x square over 2 plus that new thing there, that is plus y e to the z plus y to the 3 over 3 plus h of z. Each time you find something, go back into the function. So there is one more thing to find, that h of z. How do you do that? What is the one thing that we haven't used yet? R. And to get that R, what should we do? Find partial of f with respect to z. That's going to be xy plus 0 plus y e to the z here plus 0 plus h prime of z. And that's equal to the r component, which is xy plus y e to the z plus c to the 3. Okay. I know you've forgotten the starting problem, okay, that vector field had a third component, which is r. Again, happily cancel these. H prime of z is z to the 3. So h of z is the antiderivative, which is z to the power of 4 over 4. Now you have plus c. Now, since I'm not in a mood to repeat this whole function again, I'm just going to erase this and just copy and paste there. Okay. There you have it. That is the beautiful potential function for this vector field. So you can see it came in bits and pieces. Okay. Started off with this incomplete piece here, that got filled in here, had an incomplete piece here, got filled in there. All right, so that is a lot of hard work. Okay. So how is this useful for solving the next part of the problem? It says the particle is moving along a straight line from 300 to 003, and then from that point to some weird point pi pi pi. Whether it's in R2 or R3, the fundamental principle is the same. Okay, it's the potential function at the terminal point, which is in this case, it's ending at point where all the coordinates are pi. Okay, there is nothing wrong with that. Minus f of was it 003 or 300? Almost. So it's a fun thing to do now. Put pi's everywhere. Okay. So it's going to be pi to the power of 3 plus pi e to the power of pi. Please don't calculate anything. Plus pi square over 2 plus pi e to the power of pi plus pi to the power of 3 over 3 plus c minus x equal to 3, y equal to 0, z equal to 0. So this term is going to survive. This is going to survive. That's it. E to the power of 0 is 1. Okay. So it's 3 plus 3 square over 2. If you really believe in beautifying the answer, you could probably adjust some of those terms, but I think we have done enough work on this problem. We can stop there. I said stop with this problem. So yeah, I mean, if somebody really wants to make your life complicated, they could give you a question in R3 and ask you to find the potential function. Okay, this takes more time, but I think if you do it in R2, that is more than enough for me to know if you understand this concept. Okay, so that kind of finishes 4.3, which is one of the important sections. Now, from now on, everything is important. Okay, there's nothing. 4.2 was probably the introductory section. Now that we have hit the critical concept of vector calculus, okay, now let's see what else we could do with it. All right, any questions about this example? Oh yeah, sorry. Oh, that's the one. Oh, wait. And they cancel out. Yeah. Yes, this it's C minus C. Yep.
Why don't we just use the 2 points, pi, pi, pi?
Why?
Yeah.
Because it's a conservative vector field. It doesn't matter how you reach there. You're starting at 3, 0, 0, and you're ending at pi, pi, pi. And whether you travel along a straight line or a circle or helix or parabola or whatever it is.
So I don't know if, so in the question it says a long straight line from 300 to 003, and then a straight line from 003 to pi, pi, pi. That's for 2 separate things.
So it's starting from here, 300 to 003. And from there to, is it a straight line from there? Yeah. To pi, pi, pi. So you're going from Boston to New York, New York to Philadelphia, wherever you want. So we don't care about this part. We only care about where you start and where you finish. So the question may have a lot of distracting information there, that you need to kind of weed that out and stick with what you need. These questions are infamous for distractions, so just be careful. Any other questions? All right, so let me kind of repeat that concept here once more. I don't know which one I was pulling up and down now. Anyway. I hope all of you have finished writing this. I kind of reiterate what we have been doing. Okay, it's a lot of things coming in a gap of a couple of days, so you need to keep your thoughts collected here. Integral along C f dot dr for a non-conservative vector field is what you saw in section 4.2. Okay. Take any random vector field. If you want to do that, you have to sit down and do the integration. You could do it using the parametric form. Or we could just use the xy notation that we did yesterday, pdx plus qdy. Either way, you have to do the integration because there is no other alternative here for a non-conservative vector field, because it really matters how you go from point A to point B. If you take a semicircle and a straight line, you have to count each one of those. Okay. If it is a conservative vector field, that will be just equal to f final minus f initial for vector field f equal to pq, and if q x minus py equal to 0. That is what we just did. Okay. So I'm kind of staying with R2 for now for a reason. So that is what you call as the fundamental theorem of line integrals, because it looks like the fundamental theorem of calculus, okay, where you find the antiderivative and plug in the points from the two limits. So this is 4.2, that is 4.3. My question to you is this: if C was a closed loop with some orientation, I don't care, you can go counterclockwise or clockwise, that's your choice. Okay. If C is a closed loop and if F is conservative, very important statement here, F is conservative and C is a closed loop, what is the line integral of C of F along this particular loop?
0.
Okay, so I got an answer here. People on Zoom, any contributions about what?
0.
It will be equal to 0, because no matter where you start, okay, you can call this as point A. You go around this and you come back here. It's going to be f of A minus f of A, that's equal to 0. That's a very strong result. That's what we call as the, in electrical engineering, it's called the Kirchhoff's closed loop law. That means the total change in potential across a closed loop, not always, in a conservative electrical field is always equal to 0. Some students just ignore the conservative part and get into all kinds of trouble. Okay. This is only true for a conservative vector field. So the next question is, if you had the same closed loop and if the vector field is not conservative, what happens? So F equal to PQ, next. We need to understand the flow of topics here. We started with some generic stuff, went down to conservative, then conservative on a closed loop, now non-conservative on a closed loop. So F equal to PQ, which is not conservative. In other words, you have some net curve existing here. Okay. That is a measure of the rotation of the vector field. And if C is a closed loop, and for our sign convention purposes, let's assume that counterclockwise is positive. Okay. That is the universal notation. So this is a positively oriented closed loop in R2. Okay, so your favorite circle, rectangle, parallelogram, all those are closed loops in R2. What is the line integral of F dot dr? Now that is not zero, okay? Because the zero is a case only for a conservative vector field. Now we're talking about a non-conservative vector field, which means that there is some kind of a rotation happening here. That's a non-zero curve, okay? So it's as though there are things that are going around like this. So for this case, when you say non-zero curl, it's as though there are small fans inside it which are just turning the air around it. Intuitively, it would make sense that if you were to walk around this loop, no matter what the shape is, it could be a circle or some weird shape. Okay, if you were to walk around this loop, whatever effect of the vector field you feel is the same as whatever rotation you are feeling inside that region. Okay. So the work done by F along the loop, it's a closed loop now. Okay. It's the same as the net circulation that is generated in the surface which is enclosed by that loop. If the circulation is zero, well, we are back to a conservative vector field. Okay. But now it's not a zero circulation. There is some kind of circulation going on there. That is what is contributing to the work done. So it's a net circulation generated by the vector field F in the 2D region, okay, which is enclosed by that closed loop C. That's the next important concept we are going to learn. Okay, if you walk along a closed loop for a non-conservative vector field, the net work is the net change in circulation that is felt inside the loop. Well, it comes with a name. Okay, it's called the Green's theorem. So it's the first of the three big theorems you are learning this year. Just make some clean space for it to show some respect. In section 4.4. So next week, we'll be looking at another theorem called the Stokes theorem. Okay, that is actually a 3D version of this one. So if you understand this, you should be able to get some intuitive idea about what Stokes theorem means. These are not easy topics, so just pay attention. So let C be a counterclockwise oriented that is how we fix the orientation here. Okay. Again, that's all based on experiences from electricity and magnetism, the counterclockwise, which goes against the direction of flow. Okay. So let C be a counterclockwise oriented curve. I missed the key word, closed curve. If it's not closed, that's a different story. So don't abandon it, but at least we have to do something extra. Okay. So let C be a counterclockwise oriented closed curve in R2. That is what you mean by something like this. So for our calculation purposes, it could be a circle or a triangle or a rectangle. Okay. And let capital R be the region that is enclosed in the closed loop. R be the two-dimensional region which is enclosed. It's not a secret that any closed loop will have some kind of a surface trapped inside it. Okay. Enclosed inside C. Let F equal to PQ be a vector field. in R2. And throughout this course, we are assuming that these functions are all well defined. So P and Q are both continuous and differentiable. Then the integral along C, f dot dr. Those of you who have probably taken some physics, you might have seen some kind of a loop around it. Okay. That just says it's a closed loop integral. So the integral along C of f dot dr along a closed loop C is a double integral of the rotation qx minus py dA on the surface R. So this is the curve, the 2D curve. What I'm saying is that if you add all those small rotations in there, that upper picture there, okay, that is what is going to generate the net work done along that region, which is what you feel if you walk along the boundary. Of course, if this is 0, it's 0. So for a conservative vector field, it's still equal to 0. This is mostly attractive for a non-conservative vector field.
Curiosity, since most of these like closed areas close by curve, would we use like polar coordinates to do civil?
Yeah, some of them, depending on what we end up with, we might have to use polar coordinates, or now we have all the tools, you can use whatever you feel is appropriate. That's why we did all those things in chapter 3. Now you can pick whatever tool you want. Your toolbox is right there. So it's a question of your expertise now. You see some terms with x squared plus y squared, you know polar coordinates. All right, so the key things here, this is a counterclockwise oriented closed curve. Okay, counterclockwise is positive. So if for some reason, if your question gives you a clockwise oriented curve, clockwise, then it's going to be a negative of whatever I wrote there. Okay. Happens once in a while. Sometimes you're kind of going in the opposite direction, so the answer will be negative of what you get. But counterclockwise is positive. It must be closed. Okay. We will be dealing with a lot of cases where it's not closed, but to start off, it must be closed. And right now, this is only theorem you know, but next week you'll ask me, how do we know if you have to use Green's theorem or the other theorem? So Green's theorem is only applicable in R2 because the other two theorems is in R3. All right, so do a few examples today, a few examples tomorrow. Okay, we all should be experts in Green's theorem by the end of section 4.4, at least in doing these problems. Okay, we are not doing any mathematical proofs here. So the purpose here is to just do these problems which are suited for certain regions in R2. All right, so let's do some examples then. Before we go into the worksheet, which are mostly old final exam problems, okay, let me just do a couple of examples from the textbook and then while I try to unearth this, do you have any questions about Mr. Green? All right, so let's see. One thing that you might think is, why would somebody, instead of doing a single integral, do a double integral? Okay, that might sound crazy in the first place. Who would think that this is easier than this? That's one of the things I'll show you. It's a difficult concept to get used to, but by the end of this week, you all will be fans of Green's theorem. Just can't reach that page. Oh, here it is. Let me just pull this up. All right, example 1. Suppose we have this following vector field f equal to 4y plus the natural log of 1 plus x square. Now you see all kinds of bad things coming into this vector fields. 6x plus e to the power of y square sine y. Calculate the work done by this vector field on an object that starts at 0, 0, travels along a line to the point 1, 0. So this is the orientation being set up. Okay, so write this carefully. It travels along a line to the point 1, 0, and then travels along another line to the point 0, 2. And then back to the point 0, 0. Okay, that is how it finishes a loop. So it starts at 0, 0. The picture is pretty simple. Starts at 0, 0 here, goes along a line to the point 1, 0, then to the point 0, 2, and back to the point 0, 0. Loop. Yep.
So this is going back to my question earlier. So when you draw curves or closed curve C, you typically draw them as like, not straight lines. So like if we had this region, would we have to perform 3 integrals because it's not differentiable at 0, 0, 1, 0, 0, 2?
If you were to do this along, no, when you're doing the integration, you're okay. You just need to remember how you did you just have to parameterize each of these straight lines.
Okay.
Yeah. So we could do it. I wouldn't want to do it. For one reason, I don't like these functions here. Now here is something to remember for the next few lectures. Okay, so it's a pretty short semester at this point. Whenever we see these bad terms, there should be something in the problem to get rid of those things. Okay, this is usually a hint. These are really bad terms. Okay, nobody wants to integrate these terms. So the bad terms mean that we shouldn't be dealing with them. Okay, so if you were in an adventurous mode, you could parameterize each of the straight lines and go integrate this, going to get into all kinds of situations which you don't want to. So use Green's theorem because it's closed. I know these problems might look a little artificial because the idea is to make the concept clear, not to drown you in calculations. It's a good candidate for Green's theorem because it's a closed loop, okay, and it's counterclockwise, so the orientation is okay. So this is the C here. C is built with all these 3 lines. So the integral along C, f dot dr equal to the double integral, not the single integral. Okay. Inside this region R, which is actually a right angle triangle, okay, of qx minus py dA. Not qy minus px. That'll be a bad thing to do. Okay, qx minus py. Who's going to tell me what qx and what py are? Qx is 6, py is 4. See how I kind of avoid the bad things. 6 minus 4. I won't ask you what 6 minus 4 is. Now this is where you need to be a little bit aware of what's going on here. Okay, think back into what we were doing earlier. This is 2 times the double integral of 1 dA. I think I mentioned this many times. When you integrate 1 in a region, that tells you the area of the region R. This is from chapter 3. The triple integral of 1 is the volume, double integral of 1 is the area. Now, to not disappoint your middle school teachers, what is the area of this right angle triangle? All right, so what is that? 1. Okay. The area of this right angle triangle is 1/2 times base times height. We don't need any double integrals to do this, okay, because that's a constant number there. So that's equal to just 1/2 times base is 1, height is 2. If you want to do it, that's 1. Okay. So this answer is 2 times 1, which is 2. Things get dangerously simple now. I know the problem was probably rigged to make it happen, but the point is that you can avoid going along these 3 lines, just go right into the region that is trapped inside and do this. All right. Any questions on how that all just suddenly collapsed? Okay, let's do another example. Here comes another crazy vector field. So example 2, f of xy equal to 6x square y plus 2y to the 3 plus tan inverse of x square and then x to the 3 plus 3xy square plus e to the y. And consider the curve which starts at the point -3, 0 and goes clockwise along the circle of radius 3 centered at the origin. Okay. So clockwise, yeah, like this. So it starts at -3, 0 and it goes clockwise like this to the point 3, 0. And then it goes along this line back to the point -3, 0. Thus completing the loop. Find the integral along C. C is this entire curve. Okay. F dot dr. Can you look at this vector field and try to set up the Green's theorem equivalent of that on the right hand side for this region? It's a semicircle. Okay, so we could use Green's theorem because it's closed in that semicircle. Okay, just don't forget it's a clockwise oriented curve. Okay, it's negative for clockwise. I'm going to write down the qx and py terms and let me know if I'm making any mistakes. So it's 3x square plus 3y square for qx minus py is going to be 6x squared plus 6y squared. You know where this is going. So the curl component of this would be negative 3x squared minus 3y squared, but with this negative sign outside, that kind of negates it out. That's going to be 3 times double integral over r x squared plus y squared dA. Now, I know the previous example is probably still in your mind. Okay. There we were lucky. The curl component was a number. So that's why we could pull it out. Please don't pull out these two guys here. Okay. That's not right. So what do you do here? Polar coordinates, okay, because it's a semicircle, x squared plus y squared. I think you wrote your test number 2, but you recently did not forget all these. X squared plus y squared equal to r squared. R goes from where to where? Let me see. 0 to 3, because radius cannot be negative. Theta goes from, in polar coordinates, theta goes from 0 to pi. Those things don't change. So Green's theorem is already kind of adjusted to all the sign conventions elsewhere. So you just need to follow your usual things in polar coordinates. So don't double negate it. Okay, that negative is already taken care of. All right. So and dA is r dr d theta. Okay, so this is, you can now separate it if you want. 0 to pi d theta and 0 to 3. You have r squared times another r here. Okay, that's going to be r to the 3 dr. So that's r to the 4 over 4, which with 3 would be 81. So the final answer would be 3 times pi times r to the 4 over 4 from 0 to 3. That's 81 times 3, 243 pi over 4. Oh, okay. So okay, so if things are closed and given to you in a nice form, okay, applying Green's theorem is pretty straightforward. My question is, what if this was not fully closed? Okay. So question, the previous case there. Okay. So C is that curve, okay, which is not fully closed, and you have F being this really wild vector field. Okay. There's a nasty S in terms that you don't want to typically integrate by going along that curve. Okay. Can we still use Green's theorem? So to get a little creative here. Okay. Mm-hmm.
The word done and subtract straight line or whatever you add into the closed loop.
Okay, so that's the idea here. Okay, so if it is not closed, close it using some suitable curve. Okay. Close the loop. You need a region enclosed in that loop. That's the whole point. Okay, so close the loop using an EC curve in the same orientation. That opens a can of worms. When I say EC curve, what is that? You could close like this, could close like this, you could close like this, or you could just go EC and close like that, which is the easiest of these. Sort of a trick question. Among these four curves, which is the easiest? The straight line. Okay. That would be my choice. So the EC curve is typically a straight line. Do you have a question? Yeah.
So if you were to just complete the circle, you wouldn't be able to divide by 2 unless you were integrating 1, right?
Right. You have to then, that's a bad idea because then you have to integrate it along that curve and then divide it by 2. So we are trying to avoid integrating along that curve. We are trying to use a region inside. Yeah. So the only way to do that is to somehow close it appropriately. Okay. All these are options. The easiest one is to use a straight line to close it out. So stick with a straight line, life will be easy. But you should maintain the same orientation. If the curve is clockwise, the straight line should be clockwise to close the loop. Okay. So if the triangle in the previous example was this line and this line, then the third closing line should be in this way so that you can close the loop. It's all about what could close the loop appropriately, but maintaining the same orientation. Okay. So if you had a rectangle like this, this is the closing side. So do Green's theorem on the closed loop. And then, as I said, subtract the contribution from this extra edge that you added in. Okay, that was not in the problem, so it shouldn't show up in the answer. And subtract the work done along the closing edge. Usually that would be easy to do because you're either on the x-axis or the y-axis. A lot of things are convenient to do that particular integral. Okay. So this is the idea. The integral along C f dot dr, which is not perfectly closed. What you do is add a closing side. Let's call it a C1. Okay. All those straight lines I drew there. Did I erase that one? So this is the integral along C plus C1. Okay, that is the new closing edge that you're adding to the surface. f dot dr. Okay, now it is closed, minus the integral along C1 f dot dr. Because that was not there to start with, you have to take it out. And this part is your Green's theorem, which is the double integral over R of qx minus py dA. Don't forget to put a negative, which is clockwise, minus this extra thing. And this part here will always be of the form p dx plus q dy. That is why I did that non-parametric thing yesterday. Okay. So if f is pq, dr is dx dy, f dot dr is p dx plus q dy. So if it is along the x-axis, then dy is 0, and along the y-axis, then dx is 0. That is why we are very clever in picking our closing edge. Okay, we keep it on the axis, so only one of these terms will be active. So the integral is now pretty straightforward to compute. So it's very important that you close it properly. Okay. So if you close it along this one, along the y-axis, then dx equal to 0. If you close it on the x-axis, then dy equal to 0. It's very rare that you will see a problem with closing edges along some arbitrary lines. It's always going to be either on the y-axis or the x-axis. All right, so that is going to be our main highlight tomorrow. So we will do all those problems in the worksheet, which are all kind of in this pattern, okay, where you have semi-closed regions, and we can conveniently close them and apply Green's theorem. All right, so that's it for today. I have office hours from 12:10 to 1:10. If you have any questions about tomorrow's quiz or anything. I'll see you tomorrow.